We are beginning Unit 11, and in this unit we begin our look at sequences and series. So let's begin by talking about sequences, and for this you have a packet of notes that that goes through this whole unit. First of all, a sequence is a function whose domain is the set of positive integers. Okay, and it's in a list. Each of the terms in the list is separated by a comma. All right, so it's not a sum, it's not a difference, it's not a product, it's just a list. Okay, a sequence is a list. All right, the a sub n term is called the nth term, and the sequence is denoted by this notation. This is a form of notation that we can use to represent the entire list. Okay, the subscript n is understood to start at 1 and to include all positive integers. So 1, 2, 3, etc. Okay, and that's what a sequence is. So first of all, let's look at a couple of examples of just getting a feel for what a sequence is. So write the first 5 terms of the sequence whose nth term is given by a sub n is equal to 3 to the n. So the first term would be when the subscript is 1, so the first term would be 3 to the first, or 3. The second term would be 3 to the second, 3 to the third, 3 to the fourth, and 3 to the fifth, and those would be the first 5 terms of the sequence. Okay? In part B, we have this sequence. So the first term would be when n is 1, so we would have 2 over 1 factorial. The next term would be 2 over 2 factorial, 2 over 3 factorial, 2 over 4 factorial, and 2 over 5 factorial. So in this unit and in the next unit, we are going to be using factorials quite a bit, and it will be good for you to recognize the value of these factorials. So if this was a free response question, you could totally just stop here, and this would be a valid answer. But since we are going to be wanting to get familiar with these factorials, let's go ahead and simplify this. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And then 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Okay? And then we could simplify these further, but I just wanted to get a feel for these factorials. We could simplify these as well, right? And I say simplify. We could change these to another form of their value, right? Okay, example 2. Last year when you took a look at sequences, you talked about arithmetic sequences. And an arithmetic sequence has a common difference, which means if you take any number in the list, if you take any a sub n and you divide by the, not divide, you subtract the term in front of it, you should get the same number every time. So it's called a common difference because a sub n minus a sub n minus 1, so the term in front, will be the common difference, and we usually called that D last year, right? So 18 minus 13 is 5. 13 minus 8 is 5. 8 minus 3 is 5. Okay? So another way to think of the common difference is you add that number to get to the next term. You keep adding that number to get to the next term. So even though they didn't put the term after 18, we could find out what it was by adding 5 to it, right? So that's the common difference, and that is an arithmetic sequence. You also looked at geometric sequences last year. So a geometric series has a common ratio. This says ration. It's not ration. It's a ratio. Hopefully I'll fix that. But I'm pretty sure I said that to my kids last year. But it's a common ratio. So if you take any term in the sequence and divide by the term in front of it, you should get the same number every time. So it's we have a geometric sequence. If a sub n divided by the term in front of it, a sub n minus 1, is equal to, and we call that r, okay? The common ratio is called r. So negative 135 divided by 45 is negative 3. 45 divided by negative 15 is negative 3. Negative 15 divided by 5 is negative 3. Another way to think of it is you multiply by the common ratio to get to the next term each time. Okay? So that's arithmetic sequence and geometric sequences. And we will learn that arithmetic sequences just are not quite as interesting to us as geometric are. Geometric sequences are more interesting to us. Okay? Some sequences are neither arithmetic nor geometric. Okay? So they don't have a common difference and they don't have a common ratio, but they still have a pattern. They still have a pattern each time. Okay? Sometimes the pattern is easy to see and sometimes it's less easy to see. Okay? All right. All right. Now, sometimes a sequence will get closer and closer to a finite number as n gets larger. As n gets larger, the sequence gets closer and closer and closer to some number. Okay? If a sequence has a finite limit as n goes to infinity, maybe the terms are getting closer and closer to 3, maybe they're getting closer or closer to 2, whatever, negative 5, whatever. This sequence, I can tell, gets closer and closer to 2/3 as it goes on. Okay? I know it does because when I take the limit of this as n goes to infinity, I know I get 2/3, right? The limit as n goes to infinity, we can just use a short little L'Hopital's rule on that. Or we can consider the fact that the negative 1 and the plus 1 won't matter. The n's can't reduce out, and we're left with 2/3. So this sequence, as it goes on, it gets closer and closer and closer to 2/3. Okay? It converges to 2/3. Converges. We say that it converges to that value. If the sequence does not have a finite limit, as n goes to infinity, we say that the sequence diverges. In this one, the limit as n goes to infinity, if we let n go to infinity, this just goes to infinity, doesn't it? So we say that the sequence diverges. Okay? A sequence might diverge because the terms are increasing without bound. That's what this one did. Or because the terms are decreasing without bound, meaning it goes to negative infinity. Or because there is no limit as n goes to infinity. We'll look at a case like that. For instance, what if it went from one number to another number? What if it didn't converge to a single value? What if it bounced between two values, right? Then there just is no limit. It's not that they go to infinity or negative infinity. It's just not there. And if it's not there, we say that it diverges. The sequence diverges. So, if you want to determine if a sequence converges or diverges, what should you do? Well, you should take the limit of the a sub n term as n goes to infinity, right? So let's take a look at some examples. So in these examples, we're trying to determine whether the sequence converges or diverges. If the sequence converges, we're going to state what it converges to. Okay? So in this problem, we're finding the limit as n goes to infinity of the a sub n term, 1/2 to the n minus 1. Okay? So we know we can apply an exponent rule. So 1/2 to the n minus 1 means 1 to the n minus 1 divided by 2 to the n minus 1. But 1 to the n minus 1 is just 1, right? Now let's let n go to infinity. As n goes to infinity, let me get another color here. As n goes to infinity, the exponent goes to infinity, so the denominator goes to, just the denominator, goes to infinity, right? So 1 divided by that denominator goes to 0. So we would say that this sequence converges, the sequence converges to 0. What about 3 plus negative 1 to the n? 3 plus negative 1 to the n. Well, we can think of the limit as n goes to infinity, but this one's a little bit more difficult to consider. If we let n go to infinity, what does negative 1 to the infinity go to? Well, we kind of consider it's going to a huge number. It's increasing without bound, right? Do we know if it's even or odd? Because that's going to matter, right? Do we know if as n goes to infinity, is n going to be even or odd? We don't know. Let's take a look at when this happens. Let's not take the limit as n goes to infinity. Let's write out some terms. The first term would be when n is 1. So we would have 3 plus negative 1 to the 1, which is 3 plus negative 1, or 2. The second term would be 3 plus negative 1 squared, which would be 3 plus 1, or 4. When n is 3, though, we're back to keeping that negative, so we're back to 2. When n is even, I may have said that wrong. When n is odd, we keep the negative 1. When n is even, though, we're going to make that a positive 1. So this sequence does this. Will the sequence converge to a single number? Will it converge to a finite number? No, it doesn't. It bounces between 2 and 4 the whole time. So we say that the sequence diverges. Okay, what about this one? This really looks a little fuzzy. I wish I could sharpen that up. Sometimes it just works. Okay, I think it just worked. Okay, let's think about the limit as n goes to infinity for this sequence. So as n goes to infinity, we can do a quick little L'Hopital's on this, right? We're going to get 3 over negative 5, right? Or you can think of the positive 2 and the 1 here will not matter in the scheme of things. They won't matter as n goes to infinity. The n's will reduce out, and we get negative 3/5. So we say that this sequence converges to negative 3/5. Okay. Let's take a look at another one. D here. All right, let's take a look at this limit. So limit as n goes to infinity of natural log n divided by n. Well, if we just let n go to infinity, we're going to get infinity over infinity, aren't we? Natural log n, the graph of natural log x, remember, does that. it does go to infinity, just very, very slowly. Do you remember back when we put in like a huge number for x in like natural log? What's natural log of this number? 18. Natural log of, let's get some more 9s in there, 29. It goes to infinity just very, very, very slowly. Very, very slowly. Okay? So, what does that mean? We still have infinity over infinity. So we can use L'Hopital's here. The derivative of natural log n with respect to n will be 1 over n. The derivative of n is 1. Now let's let n go to infinity. As n goes to infinity, 1 over infinity will go to 0. So we have 0 over 1, so this thing goes to 0. Okay? This kind of presents an interesting concept for us. When you have the limit as n goes to infinity, and you have two things that each go to infinity, sometimes you can look at their, what I like to think of as power of infinity, or degree of infinity, okay? Natural log n does go to infinity, but extraordinarily slowly. Even more slowly than the graph of y equals x, okay? So if you have two things and they both go to infinity, a lot of times you can look at, where is my power? Where's the power? The power certainly isn't up here with ln of n. The power is down here. So this behaves like 1 over n. It behaves like that, okay? As n goes to infinity. Make sense? What if we had something else? What if we had n and e to the n? Where's your power now? Consider the graph of y equals x, which would be like the n, and y equals e to the n, which, I'm sorry, e to the x, which would be like the e to the n. Which one has the greater power of infinity? The denominator does, right? So again, the power would be in the denominator, and this thing would go to 0. If these were reversed and we had e to the n over n, the whole thing would go to infinity because the power would be up on top. Okay? So this is usually where kids ask, Miss Murray, which one is the most powerful? Well, for us, the one that is the most powerful that we will deal with is n to the n. That's our most powerful. Followed shortly behind by n factorial. Those are both, this is Big Daddy and this is Big Mama. Okay? When Big Daddy or Big Mama's in the house, they're going to rule the roost. They're going to decide where infinity lies, okay? Going to control it. Next up is some number, any number to the n, like e to the n, okay? Some number to the n. Some integer to the n, okay? Next up is polynomials. So I'm going to put n, but it's any polynomial. And you know, and how about if I put n to the a? So because it could be n cubed, n to the fourth, n squared, n to any number, including 1, like that. Okay. And then last up, pulling up the rear, is natural log n. Okay. Yes, it goes to infinity, but gosh, it's slow. It is a weak infinity. So if you had your a sub n was maybe n, let's say, well, let's not make it n to the n, because what about e to the n over n to the fourth? and you were taking the limit as n goes to infinity, where's the power? They both go to infinity, where's the power? Well, this is awfully strong, but it is not as strong as e to the n. E to the n would rule that. So the infinity would be on top, and so the limit would go to infinity. Okay? All right, I probably spent a little bit too much time on that, but that's okay. Kids usually find that interesting. I do. I find it interesting too. Okay. What about sine n? What is the limit as n goes to infinity of sine of n? Well, consider the graph of sine of n. What does the graph of sine of n do as n goes to infinity? Sine of n oscillates between 1 and -1, right? So will it converge to a single value? No. This limit does not exist. Not because it goes to infinity or negative infinity, just because it doesn't converge to a single value. So this one converges. I'm sorry, diverges. This series diverges. Not series, sequence. The sequence diverges. Up here, I didn't really write this out, but in part D, I would say that the sequence converges to 0. Okay? F. What about this one? The limit as n goes to infinity of n plus 1 factorial divided by n plus 3 factorial. Well, for this one, we have these factorials, and I see a factorial on top and a factorial on the bottom, so I'd like to reduce those. So here's how to reduce a factorial. Go to your larger one. Go to your larger one. The n plus 3 is larger than n plus 1, right? So go to your larger one and expand it out until you get to your smaller one. So the first term in the factorial would be n plus 3. The second term would be 1 less than that, right? So n plus 2. The next term would be n plus 1. That's what I have here, so I'm going to not write out any more. I'm going to leave it like that. Up on top, I still have that n plus 1 factorial. What happens here? They reduce, leaving a 1 on top and n plus 3 times n plus 2 on the bottom, right? Now let n go to n go to infinity. Now let n go to infinity. As n goes to infinity, the denominator goes to infinity. So we have 1 over a huge unbounded number, so this whole thing goes to 0. So this is 0, so the sequence converges to 0. I usually abbreviate converges like that. Sequence just SEQ. Okay? Part G here is the same way, so we're taking the limit as n goes to infinity of n plus 1 factorial divided by n factorial. Let's reduce the factorials. I also like to reduce these factorials because it gets you into more factorial work, which you're going to need this unit and next unit. Okay? All right, so go to your larger factorial. That's on top here. So I'm going to write out the factorial until I get to n. So I have n plus 1. I multiply by the number, the first number lower than n plus 1 is n, right? But that is down here, so I'm going to stop there, reduce what I have. It leaves a 1 on top, on the bottom. Now let n go to infinity. As n goes to infinity, I have infinity over 1, which is infinity. This does not exist. So the sequence diverges. Okay? All right. I also included in your notes something that most Calculus 2 university courses will include. We don't do a lot of it in AP. I've never seen it asked about on AP. But I think it's worth mentioning, especially for you who are going to go into linear algebra, discrete math, some of those that this is a nice time to be introduced to these terms, okay? So first of all, a definition of a monotonic sequence. Well, that prefix mono kind of says singular or one, right? A sequence is monotonic when its terms are always increasing or always decreasing. Okay? And that's all a monotonic sequence is. So if it's always increasing or always decreasing, it's monotonic. There's also something called a bounded sequence. And there are two types of being bounded. You can be bounded above or bounded below. And if you're bounded both above and below, then you're just said to be bounded. Okay? So a sequence is bounded above when every term in the sequence is less than some number. So think of a graph. Think of this graph of sine up here. Every term is less than or equal to 1, right? So this sequence is bounded above. It's bounded above. There's no term in the sequence that goes above 1. So it's bounded above by 1. Okay? And it's bounded below by -1 because there's no term less than -1. So it's bounded above, it has an upper bound of 1, and it's bounded below, it has okay, this needs to be corrected. This should be greater than or equal to. Perfect. I'll make myself a note to go do that. Hopefully it'll be right on your paper. Okay, so every number in the sequence is larger than that lower bound, right? Every number in the sequence is larger than that lower bound. Okay? And since this sequence is bounded both above and below, it's said to be bounded. And that's all bounded is. Okay? Just to get a little practice with it before we go on, let's do a couple of examples here. So let's say this is our sequence. We want to determine if these sequences are monotonic and if they're bounded. Okay? So for this sequence, it's nice to take a look at the graph of this or the points on a graph of this. Remember that in a sequence, it's not, even though I drew this sequence connected, a sequence isn't every, the subscript here, n is not every real number, is it? N starts at 1 and then goes to 2 and then goes to 3, etc., right? So even though I drew them connected, it should be pretty, it should be pretty jagged. So down here I'm just going to plot these points. The first term would be 1 over 1, which is 1. So the first term would be like that. The second term would be 1/2. So when n is 2, we're at 1/2. The next term would be 1/3, and then 1/4, and then 1/5. That's probably enough to get an idea of what's going on, right? So, is this sequence monotonic? Is this sequence always increasing or always decreasing? Well, this sequence is always decreasing. We can see that, right? So we can say that the sequence is monotonic since it's always decreasing. We could take the derivative and see that the derivative is negative 2, right? So the derivative of this would be negative 1 over n squared, which means it's always negative, isn't it? So this will be always decreasing. So a sub n is monotonic. Is it bounded? Is it bounded? Well, is there a number that every term is less than that number, or equal to, less than or equal to that number? Yes, a sub n is bounded above by positive 1 and below by what? Is there a number that a sub n, every term is higher than? Yeah, 0. It'll never get to 0. So we can say a sub n is bounded. The sequence is bounded. Okay? Let's take a look at this one. Again, I think it's a nice idea to take a look at the graph on these. So we start when n is 1. When n is 1, we have cosine of, okay, there's another mistake here. There should be no x in there. Okay, goodness, I really need to go tweak this. Okay, when n is 1, we're going to have cosine of pi over 3. Well, cosine of pi over 3 is a half, so if this is 1 here, cosine of pi over 3 is a half. When n is 2, we'll have cosine of 2 pi over 3. Well, cosine of 2 pi over 3 is a negative 1/2, right? Cosine of 3 pi over 3. Cosine of 3 pi over 3 is just cosine of pi, right? So that is a negative 1. So when n is 3, we're at negative 1. If that's the negative 1 here. Okay? Cosine of 4 pi over 3. Cosine of 4 pi over 3 is back to negative 1/2. And it's going to keep on doing that, right? If we considered, we know what cosine looks like, right? So, is a sub n monotonic? No. Sometimes it's decreasing, sometimes it's increasing. Is it bounded? Is a sub n bounded? Yes. A sub n is bounded. And we can say above by 1, below by negative 1. Okay? What about this one? What about this one? Let's put in 1 for n. 1 for n, we'll have e over 1. So when n is 1, we are at e, right? What about when n is 2? When n is 2, we'll have e squared over 2. Do you know what e squared over 2 is? Is it bigger than e? Oops, that's not right. E squared divided by 2. It is bigger than e. It's up to 3.69 something, right? What about when n is 3? We'll have e cubed divided by 3. I'm looking for, is it bigger than that? It sure is. Almost double it, right? Almost double it. So that's probably enough to convince you that here a sub n is monotonic because a sub n is always increasing. Always increasing. Is a sub n bounded? Well, it's not bounded above, is it? It's not bounded above, but is bounded below. Okay? We could say it's bounded below by E, if we would like. Okay? All right, I'm going to leave that page out because there's a couple things I need to fix on that page. Okay. Let us go to the next page here. Next page. So now that's pretty much it for sequences. That is pretty much it for sequences. We are going to spend then almost the entire rest of this unit talking about series. And a series is the sum of the terms in a sequence. Okay? So a series is the sum of the terms. Okay? We can use this kind of notation. We see that a lot. Okay? We can use this notation. That's fine too. But these are infinite series. Okay? These are infinite series. For this unit, when I say the word series, I'm talking about an infinite series. Last year when you did it, I believe you had some finite series. Okay? Most of what we do in here is going to refer to infinite series in calculus. Okay? Another thing to note, our n for series, it can start at anything we want it to start at. Most of the time, it starts at either 0 or 1. But sometimes, because of the series, a 0 or 1 might make that first term undefined, like if you have a natural log in the denominator. So sometimes this n does not start at 0 or 1, all right? Be careful with that. Always take a look at where you're starting, okay? Sometimes it makes a difference to the question, depending on the question. Sometimes it doesn't make a difference, but in some questions it will. So just be aware of that, okay? Also, we're going to be writing the sigma notation a lot. So if you see me use sigma notation and I don't put n equals 1 to infinity, you can assume that it goes to infinity, all right? And you can, lots of times we can, we will know, you won't have to guess where n is beginning. Either it won't matter, like I just talked about, whether it begins at 0, 1, or something else, or you can tell from the context of the problem, okay? And it won't be a problem. All right. So, for the rest of this unit, we're going to be concerned with two main questions. Does the series converge or diverge? And if the series converges, then what is its sum? Okay? So what does that mean when it's a series? We talked about what convergence and divergence is with a sequence. What does it mean for a series? Well, we say that an infinite series converges if the sequence of partial sums converges to some number f. And so we're going to be thinking of it in that way, sequence of partial sums. We're going to take a look at that in just a second. If the sequence of partial sums diverges, then we say that the series diverges. Okay? Let's take a look at what that means. Let's say we're given this series, okay, and we want to know, does this converge or diverge? So let's find the first 5 terms of the sequence of partial sums. So I have this capital S, that refers to the sequence of partial sums. So let me grab my calculator here. Okay. So S sub 1 would be the sum of the first 1 term. Okay. So it would just be the first term, 3. S sub 2 is the sum of the first two terms. Okay, 3 plus 5. S sub 3 is the sum of the first three terms. 3 plus 5 plus 7. I can still do that one. Okay. S sub 4 is the sum of the first four terms. So 3 plus 5 plus 7 plus 9, right? S sub 5 is the sum of the first five terms. So I know I'm adding 11 to 24, right? Okay. What is this sum doing? I didn't have us go to the sixth term, but what would that have been? We would be adding 13 to 35, so 48, right? What is this thing doing? Is it going to converge to a number, or is it going to keep on getting bigger and bigger and bigger and bigger? Well, it is. It's going to keep on getting larger. So does the sequence appear to have a limit, or is it increasing without bound? It appears to be increasing without bound. Okay. This sequence is arithmetic, isn't it? Because we add 2 each time. All arithmetic sequences diverge. They just all diverge. So it just makes them not interesting to us. So we just won't talk about them anymore. Okay. Let's talk about this one. This one is not. Okay. So let's take a look at this one. Find the first 10 terms in the sequence of partial sums and list them below. And usually in class, I let kids get out their calculator and type it all in. So the first term would be 1.5. That would be S sub 1, right? The next term would be S sub 2, so the sum of the first two terms. So we'd have 3 halves plus 3 fourths, right? So 2.25. Okay, so the next one, we would be adding 3/8 to this, right? So plus 3/8. So 2.625. The next one we would add 3/16 to that. So 2.8125. And I'm just going to give you the rest of these. We've got 2.906. If I'm starting to round to 3 decimal places. 2.953. 2.977, 2.988, 2.994 is S sub 10, all right? So, same questions that I asked you above. Does this sequence appear to have a limit? Or is it increasing without bound? Well, it does appear to have a limit, doesn't it? It appears to have a limit. It appears to have a limit. It looks like it's getting closer and closer to 3, right? So it appears that way. Okay. This sequence is geometric, isn't it? What do you multiply to get to this term? What do you multiply by to get to that term? The numerator, you're only multiplying by 1. The denominator, you're multiplying by 2, right? To get to the next term, do you multiply by 1/2? You sure do. To get the next term, you multiply by 1/2? Yes, you do. Yes, you do. So in this one, this is a geometric series. The common ratio, R, is 1/2, isn't it? Last year, you had a way to find the sum of an infinite geometric series when the absolute value of r was less than 1. If the absolute value of r was less than 1, then you could find the sum of it, right? You could find the sum of it using a little formula that was very easy to use. The first term, a, the first term, divided by 1 minus r. And if we take this and multiply by 2 over 2, we get 3 divided by 2 minus 1, which is 3. Makes sense. All right. We are going to spend the rest of this unit learning 10 tests to determine whether a series converges or diverges, because this way is not very elegant, right? And depending on the series, this may not be very effective, okay? So instead of writing out terms like this, we will learn 10 tests. To determine it for us, okay? Sometimes we can actually find the sum too. If it's geometric, the geometric series test is one of our 10 tests. If it's geometric and converging, then we can find the sum. So sometimes we can actually find the sum, sometimes we cannot, okay? All we're concerned about is finding out, determining, does the series converge or diverge? Okay? So go get some practice doing the sequences, and join me tomorrow, and we'll talk about our first tests for convergence and divergence.